wanted to talk about a new navigational aid for flight research that I was able to work on this past summer at the NASA Armstrong Flight Research Center. Before I go into all of the details, I just wanted to talk a little bit about the motivation behind it. Many of the center's projects require very precise flying relative to an object or to another aircraft, which can lead to some very difficult maneuvers for the pilots to accomplish and still get good data for the researchers to analyze. And it's particularly hard with the current technology that we have. Airbosco, a project coming down the line, will require similarly a very high level of accuracy. I'll get into it, but basically it's trying to make the pretty pictures to the right called Schlieren images. So BOSCO was the phase before Airbosco, and BOSCO stands for Background-Oriented Schlieren Using Celestial Objects. And basically what it's trying to do is have a fixed camera on the ground, take a picture of a supersonic aircraft as it flies in front of the sun, and then take that pictures and filter it out so you get this pretty Schlieren image. And this gives all sorts of good information about the sonic waves propagating off of the aircraft for the researchers to analyze. And the reason this is important is for a project later on, which is called the Low Boom Flight Demonstrator. What that project is trying to do is demonstrate that you can make an aircraft go supersonic but have a quiet supersonic boom. And so instead of having the large clap of a sonic boom that you're used to, you have more of a thud, like dropping a box of books on the ground. And this would be very important to demonstrate because currently supersonic jets are not allowed to go over land because of sound restrictions. But if we were able to show that you can have a quiet supersonic aircraft, then those restrictions might be lifted. But the problem is, with taking these pictures, is that the low boom flight demonstrator is going to be flying very high. So in order to make up that range, you have to put the camera on the aircraft, which leads to a whole other dimension of difficulty. And it's hard to get that perfect shot that we just saw. So that's where ALIGNS comes in. It stands for Airborne Location Integrating Geospatial Navigation Systems, and its goal is to create a display with positional, velocity, yaw, and pitch information, and format it to be easily read, so that the pilots can easily adjust to get onto the right course and get to the right spot at the right time. Another project was to make the software easily modified for the future, so other projects can use it. For the design considerations, we used the Raspberry Pi 3 and the Raspberry Pi LCD display. The Raspberry Pi is a very versatile device, and it has a lot of processing power, which we needed. We decided to use the Python programming language because it is very compatible with the Raspberry Pi 3, and it can be ported to many different hardwares in case we decide to use something else other than the Raspberry Pi in the future. My personal responsibilities were to program the GUI, which is what the pilot sees, and then integrate the back-end calculations to the front GUI so that everything updated properly. And then I assisted with a bunch of other testing, as well as the integration of the ALIGNS system into flight simulators for later testing, as well as some other things throughout the summer. So before I go into the GUI designs, I just want to say that these are some older designs because the newer ones haven't been publicly released yet. So first looking at it, there's a lot of information and it can look a little overwhelming if you don't know where to look. But when you break it down, like looking at the initial input information, it's not as hard to see. This is what the pilot would first put in when he gets into the aircraft, so that he has these points for reference for later down in the mission. Then the backseater, who is going to be the one who's actually taking the pictures, not flying the aircraft, needs to look at all of this information here. And so the important things for him are the azimuth elevation, relative ground speed, and the slant distance, so he can put that in for the settings for the aircraft. And then in the top right corner you see the T minus 10.1, and that tells him when he needs to start clicking to take the pictures. And then this is the information that the pilot is going to want to look at. So this is what tells him how to get to the right spot at the right time. In the bottom right corner you can see the flight director, which is that rectangle. And this is what actually tells him if he needs to turn left or turn down, which he needs to do both in this case. He's trying to get the green lines to line up with the center dashed lines. Then in the center, there's the moving map, and this updates real time to show him where the target aircraft is and where the waypoint would be, or the intercept points to where he needs to go to take the picture. And for the center stuff, that's more for situational awareness because he has some other gauges to cross-reference with. And all of this information is going to be updated real time so that the pilot knows that all this information is good, unless the top right corner satellite image is red, in which case he knows that there's been a timeout with the satellite uplink. So in the end, we completed the software, we integrated it into the flight simulator, and we actually got to run piloted test scenarios, and the pilots gave us some really good feedback, and were able to accomplish their missions nearly every time. And I really enjoyed the summer, and thank you for listening.